Welcome to Zero Knowledge, a podcast where we explore the latest in blockchain technology and the decentralized web. The show is hosted by me, Anna.
And me, Frederick.
In this week's episode, we catch up with Juan Benet to chat about the history of IPFS, Libp2p, and Protocol Lab's incentivized decentralized storage protocol, Filecoin. Before we start off, I want to let you know once again about our listener feedback form. A number of you have already given us some great feedback, so thank you. But if you haven't yet, please do weigh in. This feedback is so helpful to inform what the next year of the podcast should look like, so do keep it coming. I've added the link in the show notes. It's a short, anonymous questionnaire, so if you're a long-standing listener or if you're pretty new to the show, we'd really like to hear from you. Of course, you can also always keep in touch with us on Telegram, Twitter, or check out our very small but growing YouTube channel. You can subscribe where you get your podcast to Zero Knowledge. We share a new episode every week. So now here's our interview with Juan Benet from Protocol Labs.
All right. So in this week's episode, we have a very special episode because it's the pickup of a series that we started like 2 years ago. It feels like 2 years ago, which is decentralized storage. And we have one of the main people in the decentralized storage story, in my opinion, Juan Benet of Protocol Labs. Welcome to the show.
Thank you. Thanks for having me. It's an honor.
And we have Anna with us as usual as well.
Hello.
So let's talk about decentralized storage, IPFS, Filecoin. There's a bunch of stuff to get into. And maybe to start out, talk a little bit about you, how you got involved in the space, what your history in this story is.
Yeah. So I studied computer science, and in that period, I'd been an admirer of a lot of the peer-to-peer technology of the kind of first wave of peer-to-peer. So this is everything like BitTorrent and Skype and things like that. And in studying computer science and distributed systems, it always occurred to me that there wasn't enough attention paid to these peer-to-peer distributed systems that achieved massive scale with relatively few resources. And there was something off always about them in that they were able to achieve this great scale out of these, kind of ad hoc networks, but never really were able to get past certain thresholds of reliability in some cases, or would rely on kind of freeloading on a bunch of resources from peers in very well-connected environments, but without kind of compensating that usage at all. Right? So when you think about things like Skype as using the bandwidth of a bunch of people around the planet, especially people with really good connections, that kind of like went sort of uncompensated. And so it always seemed to me that if you could actually apply markets to the problem, that could be a much better setup. And so that was early on. This was kind of before Bitcoin. And then after Bitcoin and the cryptocurrency movement started, that sort of coincided with some other work I was doing around data set distribution and things like that. And I started kind of thinking through, I was kind of designing a file system that was meant to work kind of like BitTorrent and Git. So imagining kind of hash-linked Merkle trees and being able to distribute that in a peer-to-peer way. And at the time, now that Bitcoin was out and we're finally getting cryptocurrencies, because cryptocurrencies have been trying to be a thing for a very long time and not being able to break through and actually become adopted. And Bitcoin was finally reaching that scale. Suddenly became possible to say, hey, what if you could just use the same kind of incentive structures to power a network like this? And so that was sort of the genesis of IPFS and Filecoin as kind of sister projects. And there was a very explicit choice to separate the two because they layer very cleanly in that one should be kind of the mode of addressing and distributing the actual data, and the other should be the way to actually incentivize the distribution and have all the mechanisms for doing that.
Yeah. And I think IPFS came way earlier too, right? Like that's many years in the making.
Yeah. So IPFS started in kind of like late 2013, 2014. And and then, Filecoin proper in 2016, 17. The idea for it was around in 2014, and the first version of the design was out then, but kind of took a detour in building out all of IPFS and then Libp2p and things like that before kind of coming back to Filecoin. I think people forget just how difficult the entire peer-to-peer space is, and so we've been, just creating a whole stack of systems that's actually able to compete in performance and quality with normal centralized services, right? There's about a decade and a half of optimization applied to centralized cloud systems that all of this world has to compete against. And that is incredibly difficult work to do for the entire ecosystem. And so that's reaching that level of quality requires solving a whole bunch of problems across the stack. Everything from how do you do better connectivity, how do you do more efficient encryption, if you move to transports like Quick, to all the way to how do you do better content routing and distribution of content, to then how do you better address all this information and deduplicate, to then how do you provide solid mechanisms for sound mechanisms for incentivizing the people to actually store your data and distribute it.
The creation of IPFS, was that done, like the way you described it is more like a decentralized space, but was it also done with blockchain projects in mind, or was it a more general project? Was it really for everybody?
Yeah, it's a more general project. I mean, it's kind of based on the similar data structure, right? So it was much more Git inspired than say blockchain inspired.
Okay.
But at the same time, it was these are the same. Ultimately, the same primitive gives you both. So being able to link two data structures with a hash as a link gives you the ability to have authenticated data, and especially allows you to kind of chain these data structures into these long, very large tree structures that then give you verifiability across the entire thing. And so that's an extremely valuable, powerful property. And so the same kind of thing. So this content addressing thing give us things like BitTorrent and Git and Bitcoin, and then now like the entire crypto decentralization movement. It's a very incredibly powerful primitive. And so that's IPFS is based on, building a traditional computer science oriented file system with that idea.
I want to talk a little bit about IPFS and a little bit what it is, where it came from, maybe talk about some use cases before we move on to some other stuff. So IPFS, Interplanetary File System, if I'm correct.
Yeah.
P2P file system, you just described it a little bit. It's content addressed, it's P2P distributed, but there's also like a bunch of other things that you can do. You can pin content, which means like I'm responsible, or like I say I'm going to rehost whatever someone else is hosting, but at the end of the day it's still like hosted by a person. It's not uploaded to a cloud or anything anywhere. So if we just break it down a little bit, how does IPFS work on starting from a networking layer?
Yeah, so the content model of IPFS is something that often, yes, it's a bit misunderstood. It follows a model similar to Git, in that if you have some content and you add it to your IPFS node locally, you now just have it in your node and that's it. But you're now making it available to other people in the network to request from you. If other people are interested in it, and if you give a link to other people with the hash to this content, then they'll be able to fetch it from you. And in the future, we'll have some kind of policy structure to be able to decide whether or not you give it to a certain person. But so far, that hasn't been kind of high in the priority request list. And then at that point, once you've distributed the content to another party, now they have it as well. And so you could leave the network and that same exact content would continue to be shared. So the big thing here is, say, what if you had the web, but where the address that you go to find the content is not a location, like it's not a specific computer that somebody runs, but it's actually just the identity of the file, right? So this the content address of the file. And then any computer that has the content could serve it to you. And so at the beginning, you add content to your node, it stays locally. Once other people start requesting it, and then it starts spreading through the network. Now, people could decide to keep it around or delete it and so on. And so if nobody's interested in the content, it'll disappear. If people are interested in the content and interested in keeping it around, then it'll just naturally stick around and people will serve it.
What is the default config here? Because I remember that it's like a caching structure almost. Like once I've requested it once, my system just by default keeps it around for 2 days, and then it gets automatically deleted.
Yeah, I think the defaults right now are that if you pull it, you cache it, but it's not pinned. So pinning here means I'm flagging this content to stick around in my node, and I want to keep it through kind of garbage collection, right? So when you view something and you download it, you have it locally. If you don't pin it, explicitly, then the next time garbage collection happens, it'll get deleted. And then that garbage collection happens. It's basically triggered by running out of space. There's like some space allocation that the node has. And so it just keeps things around. It caches them until you need to get rid of them.
I see. But I mean, even if you said that, the content is only around for 24 hours, if we're talking about a website like Facebook that's requested thousands of times per second, then it's basically never going to be allowed to leave the cache.
Yeah, exactly. It just sticks around. And all of those thousands of requests don't have to go out to some other machines. Like they can just operate locally and potentially offline, right? So you could, one of the benefits here is that once you have the content, if you have all of the content related to a website or an application or something like that, you can actually disconnect from the rest of the network and continue operating on that content just the same, right? So the experience is is pretty cool, where you can be looking at a web page on your browser, like an actual app, like normal HTML5 web app, and be just working with it and disconnect from the rest of the world and continue working it just fine, and then kind of connect again, right? And I think that's how the whole distribution model works.
Going back to this like earlier decentralized series, we had talked about like BitTorrent and this like, and we might have even answered this question or asked this question, but it was this idea of like breaking down content or storage data into smaller pieces and sharing them across. IPFS doesn't do that, right? Like this is like
it does. So
it does. Okay.
Yeah. So the way it works is that we call this chunking. So whenever you have files or a large database or something, that usually is represented by some internal data structure. And so in the case of normal files, which are kind of this long sequence of bytes, your operating system is splitting that up into little chunks, and then there's some tree structure around it. Now, when you upload that somewhere, that tree structure doesn't go along with a file. It's just a long sequence of bytes moves through. In IPFS, what we do is we chunk that and create this tree around it and with this index. And so each chunk is some fixed size, some small size. And all of these little bits are put into a tree, and that whole tree now represents your file. So when you request a file from me, you first look at the root. My link to this file will be like the root of this whole tree structure. And when you start trying to view it, you'll first request that node, and then you'll go down, you traverse down to the first block, get that, and now you can start viewing the file, and then you fetch the rest. So this lets you do things like immediately get the first few bytes and start displaying those in an authenticated way, and then send the rest. Because the problem with only sending a large thing is that if you only send like the large file, then you can't view it until you've downloaded the whole thing and you've been authenticated because you have to verify the hash, right? So if you only have one hash for like say a gigabyte file, or even a megabyte, you have to download that megabyte or gigabyte before you can check the hash, and then you can display it. So if you chunk it instead, you can start doing it incrementally. It also gives you fast seek. So like you could fetch the first part of the file or the middle or some specific spot without having to get everything.
But is it still like, would all of this data still sit with one quote unquote client, like one person, one computer?
Yeah, I mean, so I guess the question here is like in BitTorrent, the way this gets downloaded is you can fetch each chunk from individual peers. Like if you have 100 chunks, you can connect to 100 peers and download one off each person.
Yeah. And with IPFS, you also have, so we tend to think of this as random access. So a lot of the IPFS work has moved us into data structure land and programming language land. I'd like to dive into that a bit, but you can think of each of these chunks as having a hash associated with it. And we call it a CID, so a content identifier, because it's a hash and a little bit extra information. And so each of these chunks, whether it's like a tiny little leaf or one of these intermediate nodes in the tree or the root or something like that, all of those chunks are individually addressable. And so you can have random access into any part of all of the data. And so what this means is that if I have, say, a large directory with a lot of files in it, and I have it in IPFS, and I share a single file with you, now you copy that one file over, and you can have a different directory with a bunch of files, but that subpart is the same. And so we are both distributing that subpart together. So if another person tries to get that file as well, then they can get them from either you or me.
So then is it very, very similar to like a BitTorrent-like structure, or is there a difference? Like the chunks that you describe, are they different than whatever the breakdown would be in a BitTorrent?
Yeah, they're different. So BitTorrent chunks things kind of, it takes a large file and it then chunks it in with the same size. and then it treats all of these little things as pieces, and then you can move around these pieces and then kind of assemble the whole thing. In IPFS, we think of it much more as the tree structure of a file inside of a file system. And that data structure gives you the ability to have like seek into this. So you don't have to download the whole thing. You can just seek into a part of it. And it also gives you the ability to update this thing. So you can think of how a file mutates over time. So you can have one version of the file and then you go and change the middle or something. And then, so the new data structure is only going to have a few parts of it changed, like only the middle block and then the path, the nodes all the way going up to the root. And so you can have these different versions, and you can think of it as sort of version controlling all of this data.
Cool.
Where this gets really cool is when you start applying this to other things and files. So, for example, if we go look at other kinds of things that are not files for a moment, and we think of, say, CRDTs or just any kind of database where you have some set of objects that are linked to each other, and you start applying this hash linking to them, then you can distribute all that stuff with IPFS. And so including blockchains. So for example, you can move around blockchains with IPFS and address all of those individual blocks or transactions or all that stuff with the same kind of links. So you can have native browsing of a blockchain in kind of like a file system path-oriented notation and look at it through your web browser just natively on
What? You just mentioned CRDT. I actually don't know what that stands for.
A CRDT is a conflict-free replicated data type, or a convergent replicated data type. A couple names for it. It stands for CRDTs are these data structures that give you the ability to represent data in multiple devices, so in multiple computers, and allow updates to both in both places that converge over time. So, for example, say if you're editing a document in something like Google Docs and you're making some edits and somebody else is making some edits at the same time, you can both have a consistent view of the document and then send your updates to each other. And the data structure backing the document is designed to converge. So all of the updates are going to be applied in the exact same way. There's not going to be a conflict. And so we can both type at the same time and we're both going to arrive at the exact same thing. So Google Docs doesn't use CRDTs. They use an older thing called an operational transform. But CRDTs are effectively like the next generation version of that line of work. So you can take these data structures that can be used for these kinds of like real-time collaborative applications and just put all of those on top of IPFS. So things like an Etherpad style thing.
That's cool. This is something that like a user would actually notice. Like you as a sort of maybe even non-technical user of something like this would actually see the benefits of this thing. You just started to talk about like the way that IPFS and blockchains are used together. So you gave this one example, but are there other examples? Like, because I mean, IPFS is, I hear it constantly being cited as like the thing that's being used to deal with storage. But I bet there's so many ways in which it could be used.
There are a bunch of different ways to use it. So one way is, probably this is one of the number one uses for things surrounding blockchains. People will have some application that relies on a contract associated with a blockchain, and it'll need to address some data. And that data might be a file, or it might be a website or something like that. And so they'll take that file or that website or whatever and put it into IPFS, generate a single hash for that because it represents some tree. And then now they can put that hash into a contract. And so it provides the ability to kind of accumulate information and make it accessible or be able to operate on it inside of a contract. Now, a contract right now today can't pull data out of IPFS and operate on it. And that's where Filecoin is headed. But that's kind of one of the use cases at the moment, just being able to kind of address information. The other use case is if you have a web app this way, you can then put the code that interacts with the blockchain inside of that application in IPFS. So now you can have a dApp that moves around the IPFS network that interacts with the blockchain through some kind of API.
Interesting. But this would be like the front-end code. This wouldn't be anything. It's just sort of interacting, like you said, interacting with.
It could be the front-end code, or I mean, when you think of something like a chat application, you don't need much of a backend. You only need to distribute the information. So as long as we can both find the log of content, then that's all we need. So I can have a chat application which is just the front end, you can have a chat application which is just a front end. We can find each other in the network, and once we find each other and are interacting, then we replicate the content to each other, and that's it, and that's all we need. Now, of course, if we both delete our applications, then we've lost the data.
I want to talk a little bit about networking. So IPFS, as far as I know, uses Kademlia to find content. I guess it uses a DHT to find peers.
Yep.
But all of this is kind of tied together in something called Libp2p. Where did Libp2p start? Did it start before IPFS or like through IPFS or something else?
Yeah, so Libp2p was extracted out of IPFS, and it was sort of the lower level networking stack from IPFS. And kind of the idea for it started very early on. So as I was starting to make IPFS, it was pretty clear that all of the problems in the networking side that we were going to have to solve were pretty general and pretty applicable to a lot of other peer-to-peer systems. And there wasn't a really solid peer-to-peer library out there that we could just rely on and use. And so we said, hey, we'll just have to build it. We'll just have to write this thing and then eventually kind of turn this into a library. And in 2014, maybe 15, I was talking to Gavin and Vitalik when they were building Ethereum, and this was like before Ethereum had launched. And they were running into it, like going to have to write all this peer-to-peer code. And at the time we talked about like, hey, maybe you should just look at extracting this stuff and kind of form some common standards and then write the same library. And that way we can just reuse the same stuff. And they sort of handed this problem off to somebody who was working on the networking stack at the time. And then due to like, I think timelines and so on, just didn't match up. And Ethereum ended up using that idea to then form Dev2p. I think at the beginning they were calling it Libp2p as well. And I was like, wait, hold up. Like now we have a name conflict. It's not the same library anymore. And they're not going to interop. And now we have a name conflict. So they renamed it to Dev2p. But it was kind of like a missed opportunity. And we all saw that as a big loss in that we should have just made that the same thing from the get-go.
I think it was pretty recognized at the time too that Dev2p was a trade-off, exactly like you say, to ship something faster, where they kind of went, we don't need to be completely generic. We don't need to be completely backwards compatible or forwards compatible. Like we'll just ship something and then kind of make it specific.
Yeah, the pressures to ship something on time are strong. And so I think it was probably the right call at the time. But the good news is now with Ethereum 2, Ethereum is now on Libp2p, right? So, and I think the needs of Ethereum 2 are much broader and greater than for Ethereum 1. And so they're going to need a lot of the facilities that Libp2p now has. And of course, it's been years of maturing for Libp2p as well. So probably the stack that was there at 2014 was a shadow of what we have now. And now we have something like is actively used in a whole bunch of projects, live blockchains, and so on.
Libp2p is a library. Is it finished? Is it something that's constantly still being worked on? How does a library like this exist?
Yeah, so it is definitely constantly being worked on, and there's a lot that we have left to do there. In that, it's a library designed to be super modular, where it kind of breaks down components by problem. So one problem might be transports, and so there's a whole bunch of different networking transports that you might want to use, and ideally your application shouldn't be dependent on any one of them, and should all be pluggable. And so things like TCP and UDP and Quick and WebSockets, like all these things, Bluetooth and so on, should all be full kind of similar interfaces, and you should be able to like run your application over any of these. And so they sort of abstracts out all of the transport code. Then there's other stuff like peer route. We call it kind of peer routing, which is I'm part of a network and I'm going to maintain some information about other parties in the network. And I'd like to be able to find a specific party in the network. And so having the ability to search for a party and find them and then be able to establish a direct connection, that's sort of the peer routing problem. And there's a few different solutions for that. One of them is Kademlia, which is a particular DHT that gives you sort of log-n steps to find another peer. We also have things like peer discovery, which is a similar problem but different, where I just want to find out about ambient peers in the network, where I may not be interested in finding a specific peer. I just want to find peers that are maybe interested in the same content that I'm interested in, or maybe they're in the same location. So maybe they're around my device. And so being able to discover peers like that is a useful thing. And the thing about peer-to-peer systems is that usually there's a whole bunch of different ways of doing these things, like finding peers or connecting to them or finding content. So content routing is another one of these problems. What happens is people will build an application and they'll try to solve like all these problems at once. So they'll have to do peer discovery and peer routing and content discovery and content routing. And because of time, they'll pick like one solution that works fairly well for their application, but kind of breaks whenever you take that application into some other context.
Got it.
And what's going on really is that you need to break that apart and say, really like depending on how you want to use an application, you might have to use different systems and different solutions to solve each of these problems. So for example, a DHT is not a great peer routing or content routing solution at certain scales. It's just too slow. You might want to use something else, or certainly won't work inside of, say, a data center. There you would really want something much faster like PubSub or something like that. And so Libp2p allows you to write your application against these kind of problem interfaces and then be able to swap out the underlying modules to sort of fit the problem and fit the domain in which you're deploying the application.
It's definitely not a project that's ever done. It's, as you said, like there's an infinite amount of work. There's also like currently even quite a lot of problems with Libp2p, just in terms of also like not even technical problems, but like misuse problems. Like Substrate uses Libp2p. We wrote the Rust Libp2p library, and then in writing that, we definitely accidentally merged testnet DHT with IPFS DHT several times.
I remember that.
And like this is a common thing where like when you deal with networking normally, you kind of go, if I can connect to you, I have to like be your peer and be able to talk to you. So you kind of make that assumption really early on that if I can connect, then you're my peer. But in Libp2p, I can very well connect to you because everything is like generic and I can connect to anyone for any blockchain network or any other network. But you may not be my peer because you live on a different blockchain or you live on a different system entirely.
Yeah. And one of the things here is where we want to work on is how do you make it easy to make those kinds of connections across these systems in a way that's not gonna be problematic, right? So for example, if you connect to a peer there's an IPFS peer, right now that peer is going to like try to connect on a number of protocols that you might not speak. So for example, an application on Substrate or a blockchain on Substrate connecting to an IPFS peer, the IPFS peer will like try to run this bit swap protocol and it just will break and then the connection will break. But for example, the IPFS peer could be smarter and first inquire like, oh, do you run this thing? And if not, then don't try that. But then they could stay connected. And the cool thing there is that we might be able to share things like peer routing or other kind of subsets of the architecture. We're running into this very much in Filecoin land. So we're looking at having a whole bunch of different set of peers, like IPFS peers and Filecoin peers. Think of a Filecoin peer as being an IPFS peer that also runs the Filecoin suite of protocols, but not all IPFS peers are going to run those. So a Filecoin peer needs to be able to connect to any random IPFS peer, but it might not speak all of the protocols that Filecoin speaks. So you're able to now connect these like different heterogeneous groups together, but you have to be, as you say, like much smarter about the use there because otherwise it's gonna like be a kind of a bad peer situation to be like connecting BitTorrent to IPFS randomly or something like that. But this kind of thing could make interop across blockchains much easier because you could start sharing things like blocks and start writing protocols that are cross-blockchain in a pretty simple way.
Yeah, for sure. I mean, the sort of ideal bridge between blockchains, if you're talking in a bridging model, is that each of the blockchains has a like client to the other. But that obviously then requires that they can connect as a like client to that other network. So currently, I don't think anyone really attempts to do that in a proper networking style. They just kind of rely on some relayer to relay information into kind of a shell of a like client on the other side.
Yeah, I think right now there's these shells and then they use or sometimes I've seen people run programs that just run two full nodes completely independently, and it's just this really silly thing where like they're connecting. I've seen applications that mix two different chains and they have like the same set of peers that are now running two different full nodes and they're maintaining the same similar sets of connections. There's a totally duplicated work all over the place.
Yeah.
Just because that's easier to do today.
We've just talked about IPFS. We've talked about Libp2p. Both of these live under some kind of overarching structure or company, an organization. And we actually haven't talked about that organization. Is it a company, Protocol Labs?
Yeah, so Protocol Labs is a company that starts and supports these projects, but the projects themselves are sort of beyond the company in a sense that they're completely open source. All the IP, anybody can use any of it. And they have pretty open communities where there's a lot of contributors to these projects that are not part of Protocol Labs. In fact, most of them have more contributors outside of Protocol Labs than inside. Right now, the core teams are still in NPL, so I think a lot of the contribution to these happens there. But for example, Libp2p, in fact, since Parity built the Rust implementation, at that point there was a Go team in NPL, a JavaScript team in NPL, and then a Rust team in Parity. And that was suddenly, a third of the project was now in a different organization. And then now with Ethereum 2, I think there's 5 more implementations somewhere in a bunch of different languages.
Whoa.
And so now those are all different organizations. And so we're thinking right now through how to steward the protocol over time, the set of protocols in Libp2p, where we're kind of like, what is like the right structure for this long term, in that, people want to make changes and so on, whether it should be a foundation or something like that, like some kind of light structure to kind of keep changes on it separately. But yeah, the company that funds all this work and grows has been growing these protocols is a company that started Protocol Labs, and we'll have a number of different projects in the Web3 space, and so we are looking at a number of different things, from networking to file distribution to incentivized file storage to just broader research into the underlying cryptography. So now we have 3 full research teams looking at different parts of the whole stack. So we are now kind of driving some of the work in some of the cryptography, like the underlying low-level cryptography in use across blockchains, both in some of the zero-knowledge proofs work and in these proofs of replication, which is a type of proving system that we invented a couple of years ago, and that field sort of took off and has been developing with a number of other groups contributing constructions. And we do a bunch of consensus work. So consensus is one of these things where right now all of the blockchains are heavily rate limited by the consensus throughput, and we see that as a major area of exploration. And so the Filecoin consensus, for example, is a thing that's going to be pretty, like, very similar to other consensus protocols, but pretty different in a bunch of key ways. And we're pretty excited to boot that up. Like right now, you can look at the devnets that we have running, and it's a protocol that has, for example, many blocks in the same round. So different from other blockchains, we have different like linking structure. And so all of that work is all of this research around all this crypto and distributed systems is done within Protocol Labs.
Cool. I think it's a very aptly named company.
Thanks.
Protocol Labs.
Yep. Yeah, people ask, what do you do? Like, well, we experiment with protocols.
You seem to you kind of add the seed and then let it grow outward.
Yeah, exactly. The long-term goal is to be a place where we can just drive a bunch of breakthroughs in computing and maybe start and grow projects that over time kind of take on a life of their own and are kind of go larger. We, as a company, are super collaborative. We work with a number of other groups. We have a number of things we work on with Parity and other people in other organizations in the Web3 space, and also other orgs outside of the Web3 space. And we all of the stuff we make is open source, and we have like this strong we call it the default open pledge. So we did some legal work here to create a structure by which all of the stuff we make is by default open source. And so and we have like a different IP agreement with people where we either guarantee, we like either file no patents or only defensive things that are guaranteed to be defensive only. And so it's a very like different IP structure than most tech companies. And so a lot of people come to work with it.
Cool. Well, let's talk now about like kind of a flagship project. I don't know if you'd call it that, but something that you're definitely very well known for.
Yep.
Filecoin.
Great.
You mentioned it a few times, but I think we should totally jump into it. We've never really talked about this on the podcast. We hinted at it back when we did this decentralized storage series, but we really didn't dig into it. So I'd love to hear from you how you describe it today.
Yeah, Filecoin is a decentralized storage network, and it mixes a storage power-based consensus with a decentralized market. So the way it works is that it's a blockchain where, so think of it as a proof of work blockchain where the work involved is not hashing, but it's storing useful data. And so that's a really important difference. It means that the incentive structure for having power in the network and producing blocks is directly tied to how useful the network is and how much useful storage the network is providing. And so that lets us then use useful storage and kind of provide it in a market and kind of let clients and miners interact and have data stored. So clients come to the network and ask miners to store their data, and then agree on a fee structure, and then send the data over. The miner now holds onto the data and keeps it over time. And the protocol is designed to prove that over the duration of the deal. So say a client makes a deal with a miner for a particular duration of time, say 6 months or a year or something like that. And then the miner is now holding onto that data for that duration of time. And if they stop storing it, then Filecoin will detect that and be able to penalize the miner. So you have an incentive structure that and certainly stop paying the remainder of the fee. And then we're also working on things like repair on top of this, where you're able to detect the failure and correct it. But that's sort of going to come from that later, going back to time pressures and shipping and so on. Repair is an extremely interesting part of the whole equation. We're going to be shipping the network first and then kind of bringing on repair online after the fact. But it's a really exciting project. We probably ended up pushing the frontier of blockchains in a bunch of different ways. So proof of replication, as I mentioned earlier, is like this proving system to verify that you actually have the content and you're not cheating. So there's a very hard problem there in these systems where how do you prove to the network that you're indeed storing something and not just lying about that? And this especially gets hard if you can pretend to be the client too, right? So if there's an incentive for storing data, then I can pretend to be a client, hire myself, and then just store nothing. And so how do you actually solve that problem? It's a very interesting question that took a long time. So that's one of the interesting problems. Others include things like this higher throughput consensus and so on. But at the end of the day, it's all about taking all of the unused storage on that planet and organizing it with incentives to build the largest, most powerful computing storage network and kind of drive the prices for it down.
So, I mean, I think you've heard this concern many times before, and I'm curious to hear your thoughts on it. So when you say useful storage, a red flag is raised in my mind because the point of consensus, the difficulty in a consensus system is to increase the cost of attack. But if what you're doing is useful, then you can amortize the cost of that. So let's take the prototypical example in this world of saying that proof of work should be calculating molecules to cure cancer. Then if I actually find the cure for cancer while doing that, then I can sell that and make tons of money, which means that the cost of attack on the network is zero or even profitable. So there's this inherent problem that consensus should be hard and difficult and useless so that it's costly to attack it. But you're kind of subverting that a bit by making the thing useful.
I disagree with that. I disagree with that framing. So I think what you want is a system that makes it extremely expensive to reverse something. Where at the end of the day, what you want is, and this is kind of a very specific consensus systems, formalized consensus system question, which is how do you agree on a value? And the kind of proof of work Nakamoto consensus answer is you commit power that you've spent on top of a value. So think of it like I'm going to agree and commit to value X. And in order to do that, I take value X and then I crunch a bunch of hashes on top of it. And then after I've done that enough time and I've expended enough work, then I produce some other value and then send it out to the network. But the important thing here is the consensus is achieved when you spend that work on top of that candidate value. But you could be using this work to do something else. And so there are some concerns here around oh, well, like you mentioned, you could do that anyway, but also kind of reuse this value separately elsewhere.
Mm-hmm.
I don't think we've seen an attack like that ever in any of these networks. The thing changes entirely if that value is within the network itself, meaning that data that you're storing is useful in the context of Filecoin itself, meaning it's useful to store data within Filecoin. A really key question here is, so for example, if I just wanted to make sure that you were storing a specific file, and again, you could either cheat about what the file is or say that you can't cheat about the specific file, but you could reuse that storage and kind of pretend to another network that you're storing the same file. Now you could be reusing power, right? And so a key question here is making sure that it's unique storage spent, meaning, and this is sort of known as a proof of space. So proof of replication is a proof of storage and a proof of space. These are like subtly different. I'm happy to go into defining the differences here, but the point is the space spent is uniquely spent on the Filecoin network in the particular chain that you're on when you sort of seal a sector. So there's these units of data in Filecoin called sectors. And so when you seal a sector and you commit it to the chain, you're committing all of that work, and it's a huge amount of work spent on that particular value, and that adds that. In order to like go against that, you would have to do that particular work. There's also this added layer here, which is it's not just any hashes now. Now you have to have that specific data. So this potentially makes it harder in other ways, which is that if you can't, like if you were trying to long range attack the network, so in the proof of stake, you would have to like go and buy keys. In proof of work, you could always do it because it's just hashes. But in Filecoin, you would actually have to get that specific data and go and replicate the specific same sectors. And that's way harder.
Yeah.
So not only do you have to buy keys, you have to like acquire the specific bits of information. So you have to replicate a huge, vast amount of storage.
I guess the short answer to the question is it's proof of useful work, but you've taken steps to ensure that it is only useful to Filecoin.
Yeah, at least for when it comes to ensuring the consensus, as used for the consensus, only for that particular chain. So if Filecoin forks, for example, over time your storage will have to be committed to one of the chains and not the other.
There's also another aspect to this, I suppose, which when we talk about proof of useful work in the proof of work context of like running an AI model or whatever people propose, it's this idea of like you grind out more power on top of something to like back that thing. And you have to do that in perpetuity because there is no finality in Nakamoto consensus. But you do have finality, if I understand correctly.
Yeah, we basically declare finality at a particular height. So, and so this is based on like a different opinion about what's really going on with proof of work. So let me start by saying, first off, if a proof of network backed chain forked massively, meaning like imagine that with Bitcoin tomorrow, somebody produced a chain that went all the way back to Genesis, but it was completely different, like a completely different trace of transactions that had more work on it. Now, the proof of work kind of maximalist camp would say, take that chain. That's like the one true chain. Forget this other chain that we've been using for 10 years. Now, the like rational economy maximalists would say, absolutely not. We are going to keep the Bitcoin chain that represents all our transaction history for the last 10 years because the proof of work is only securing an economy. It's not like special unto itself. Like we're not interested in the proof of work. We're interested in the economy. So there's like a deeper level consensus protocol that's kind of a social meta consensus there that is agreeing on what the real thing is. And the proof of work is only giving you kind of intermediate security when you don't want to invoke this like deeper, harder, more expensive social consensus layer. And so I kind of describe this as like Twitter Byzantine agreement in that if people disagree on the chain, they're going to like yell about it on Twitter until they now agree on the new chain. And then we're going to switch all their code to point to the new chain. And so if you take that as kind of like the baseline backdrop to all of these protocols, that at the end of the day, there's parties agreeing on what economies they represent and agreeing to set certain parameters to kind of choose a particular chain, and will ignore other chains that are kind of by protocol more powerful or longer or whatever. Then you actually get to define rules that work very well within those constraints and say, hey, you can come up with a reasonable bound and say something like 2 weeks or even a month or potentially 3 months is a timeline after which the economy will not want to change its history. And so you can declare finality at that point and have a UX that says, if you find another chain that's longer and more powerful, that's forking from further back, you don't want to be on it. You actually want to stick to this one. And it's kind of a very explicit choice in the consensus protocol. The other thing is like you can also calculate like the probability of that outcome happening. And it can be, you can also draw finality at a particular height where you sort of declare it an extremely unlikely event. So you can apply both of these mechanisms and sort of force finality. Now, it could be that due to a hard fork or some problem, like maybe your country shuts down the internet on you for 5 days or something like that, you fork off for some reason, and you might need to kind of recover manually. And that's totally okay. I think in those circumstances, you do want to know that you forked. You do want to get the user to decide what economy they want to hook back into.
It's so different, this way of thinking about just going back to this proof of useful work or useful unique work somehow. So what is it exactly? What is it's not proof of work and it's not proof of stake. Like you sort of mentioned proof of replicability, but is that
replication? Yeah, so that's these things called proofs of storage, which are simple proving systems to prove that I have possession of some data. So proof of storage is like a larger class. And so one example might be a proof of data possession where we agree on some data X, and then I can prove to you that I have data X without even revealing X. Or certainly revealing X would be like the simplest proof. I have X, I'll prove it by just giving you X. But of course you might want to do something much smaller. If X is like a few gigabytes large, you only want to do something else. So then there's proofs of retrievability, where not only am I going to prove that I have X, but I also want to make it so that these proofs that I'm giving you can be used to reconstruct X in case that I'm malicious and I want to withhold X from you. Meaning, like, you don't want to be in a situation where I'm proving that I have X, but I refuse to give it to you. So proofs of space are a different type of proof where I can just guarantee to you that I'm spending a certain amount of storage space. So, for example, I commit to say that I'm going to store a gigabyte, and I generate a random gigabyte, and then I can prove to you that I'm storing that random gigabyte, and that I'm not storing some other thing. And so that lets you use storage space as a proof of work. So in a sense, like you can count on that storage being unique. So now the interesting part is combining a proof of space with a normal proof of data possession, where I would like X to be useful, not just a random string. Mm-hmm. And so the hard part of this was to create a proof of space that was also being used to store useful data. And so that's what proofs of replication are.
Are there actually different, I guess the question here is are these different activities incentivized differently? Are they different roles?
Yeah, so these all come from, these are like deeper level primitives than all these incentives.
Okay.
The cryptographic primitives that give you like this proving system. So a proving system is like this cryptographic protocol where it's a very simple idea, which usually says there's a prover and a verifier, and the prover is going to prove something to the verifier. Mm-hmm. It's kind of like the very, very general case. And so proof of work is that the prover is going to prove that the prover has done some work mm-hmm. to the verifier, usually some amount of work. Like the prover has spent a certain amount of resources, like a certain amount of computational cycles. And so the classic example is hashes, right? So I can prove to you that I've done 1,000 hashes. Or another proof might be a verifiable delay function where I can prove to you that I've spent a certain amount of computational cycles in sequence. And so I've waited a certain amount of time. And so these other kind of proofs of storage and so on are all proving systems like that are kind of low level primitives used in a whole wide variety of protocols. And a lot of these got invented to do things like spam reduction, right? So like proof of work was originally invented as a way to reduce spam on the internet, on email. And then these other kind of proofs of storage systems were invented to kind of create clouds that you could trust better because they could actually prove to you that they're backing up data. But these basically went completely unused in the normal centralized cloud environment where like kind of trust is contractual, and are now actually only being used finally in the whole decentralization space, because this is where we're using incentive structures to guarantee things, not contractual agreements.
So we're talking about all of these different proofs, and I happen to know that there is a zero-knowledge proof in there somewhere. Where is that somewhere, and like how does that work? Why is there a zero-knowledge proof in there?
Yeah, so we use snarks to prove some of the actual proofs of replication. So there are a bunch of different proof of replication constructions, and they usually produce kind of these large outputs. And so we would like to be able to do a lot of challenges and proofs on these proofs of replication, but then aggregate them and make a succinct proof so that it can go on chain in a very small, compact way. And there are a bunch of different ways to do this, but snarks are a great way to do this. They give you a way to kind of compute kind of prove that you've done the proofs correctly. And then you just take the actual snark proof and put that on the chain. And so parties can now verify a few of the inputs themselves and then the actual snark proof, and then know that the other proofs had to have been generated correctly. So that's where the zero knowledge proof is. In our case, it doesn't need to be zero knowledge in that we don't care about the hidden properties about the snark. We only care about the fact that it's a succinct proof of that computation.
Yeah, it's almost used as a compression algorithm over this large other proof. So I don't actually know the details of how proof of replication works, but there's this, I think it's called slow encoding or something.
Yes.
And it produces this massive lattice-based kind of tree that is very large. And the snark is basically just compressing this so it doesn't take up space on chain.
Yeah, so we take kind of like the source data and say that's kind of like a large amount of data, say a gigabyte or 32 gigabytes. And we apply this very slow encoding that kind of produces these layers, these graphs, and it produces them in layers. And the slow part is that there's kind of a sequential thing going on where in order to produce one node, like in this kind of gigabyte, you can think of a node being a 32 byte segment. And so think of like all the tiny little 32 byte segments and kind of producing a graph and kind of for each one of them hashing sequentially, which is a slow process that has to be done one after the other because of the hash function. But then there are these lattice structures with like multiple layers of these graphs. And one type of graph is a DRG, a depth robust graph, and then they get connected with these expander graphs. And so there's a whole large complicated lattice structure. And at the end, we now have encoded the original data into what we call the replica. And the replica is sort of committed to a specific value. So you can take the same source data and encode it multiple times if you wanted to, and you would end up with multiple different replicas that are all kind of uniquely encoded. Now that we've done that, in order to prove that we've done this encoding correctly, we have two approaches. Either we do the entire encoding inside of a snark or something like that, which would be extremely expensive, or we just kind of run a few of the challenges themselves to show that we've proved that we have stored this and kind of prove that. So we say sample 1,000 random challenges over this whole proof, and we do that computation inside of the snark. So we take like the source encoded data, and then we decode it, and then we also show that goes all the way back to the root that we committed to. And so it's that proof that we're making, that we want to make succinct, because otherwise it would be the 32 byte leaf and then like the whole Merkle chain all the way back up to the root, which would be a pretty large amount of data. So now times 1,000, that would be, it would be a large number of hundreds of kilobytes or megabytes to produce one proof. So with the snarks, we are able to compress that down to a few hundred bytes. I think it's like 200 bytes or something like that.
This is a use case for zero-knowledge proofs that we're seeing quite often, this idea of using it as a validity proof to kind of compress a ton of data down. We had Ariel Gabizon on the show a few months ago, and he's working with you guys, and he mentioned that you're also, I don't know if you're actually doing this, but he was looking at doing like recursion as well. So like you use a zero-knowledge proof to compress a bunch down, and then you combine a bunch of snarks together and do another snark on top of them. This is a sort of recursion idea.
Yeah, so recursive proofs are awesome. And I think right now our latest construction doesn't have recursion. Yeah, I think our latest construction doesn't have recursion. Maybe it does. I don't know about that. But because we've evaluated like hundreds of, so great story about like all of this work. It's we call it kind of like the proof roller coaster. Like you end up creating tons of different constructions over time that have all these different parameters and serve all these different kind of use cases. And so I think like the latest construction that we're going to ship with is not using recursion, but we have that is like high on our want to use list because it has a bunch of different properties. So you end up with a bunch of useful things out of that.
But I guess every time you design one of these systems, you then have to go through all of the problems that are going to come up with it and then weigh like will there be ways to mitigate these problems, or will they destroy the system, and then also maybe decide on some trade-offs like, oh, this is going to be less efficient but it'll be smaller, I don't know, something like that.
Yeah, so this parameter choice over the choice of proofs in Filecoin has been probably the biggest reason it's taken us so long to kind of ship a lot of this stuff, because you choose one construction and it has a certain shape, and it causes, say, maybe produces artifacts of like a particular size, and maybe that's fine. And then you kind of tweak some parameter and you say, hey, maybe like we want the sectors to be like slightly bigger. And now that makes some other parameter have to change. And so pretty quickly you're in a very large parameter space with many different variables where you tweak one thing here and a bunch of other things have to change as well. And doing that complexity management as a bunch of these algorithms are getting optimized is pretty difficult. Because a lot of these constructions, these kind of slow encoding, so you want it to be slow enough to be useful for the proof, but fast enough that it's not very expensive. And like dialing that just right is a pretty difficult challenge. And nailing that with then the particular snark constructions on top to make sure that you can do this efficiently and again, succinctly enough that it doesn't produce too much to go in the chain. All of that parameter optimization has been so intense and difficult that we actually had to write software to be able to deal with this. Meaning, like, we have a constraint solver just to be able to deal with the constraint optimization problem on choosing the proof structures and the parameters in Filecoin, which is kind of an amazing like result out of this, where a bunch of other groups can like now use that to make their lives easier. But like we had to like write this.
That was actually going to be my question. If you're actually sharing these internal tools that you've had to create in order to even try out some of these ideas.
Yeah, we use a thing called Orient, and yeah, it's on GitHub. Again, everything is super open source, so you can go check it out. It has like a special language where you define a particular algorithm, and you can think of algorithms and the artifacts it generate, and kind of composing these algorithms into larger ones. And you have like all these variables and parameters. And then you can do kind of experimental results for, say, how long certain hash functions take. And then you plug that data in as some of the parameters. And then you kind of compute out what other parameters have to be, right? So based on like this hash function and how long it takes, say, outside of a snark and inside of a snark, then like this particular construction is the one you want to use because it kind of minimizes some times and maybe it like minimizes some like on-chain footprint, and like all of that stuff is calculated through this constraint solver. I kind of think of it as like making blockchain tech right now because of how complex the structures are, both the individual primitives and the kind of how they're weaved into a chain or like all the off-chain protocols and so on. All of that stuff is so complex that we need software to help us write software. So it's kind of like chip manufacturing in a way where chip manufacturing was going pretty well until it hits a certain size, sort of kind of like density. And they then stopped being able to produce chips manually, and they had to start using software to be able to lay out the chips.
Wow.
I think we've hit that point with blockchains where some of the constructions that we're making, we need software to help us design. And to check it's correct, because the correctness there is the most important thing. Like if you accidentally mess up a parameter somewhere, then like the whole thing breaks.
I just want to ask, this is sort of a bit of a switch away, but I want to ask if you've looked at any of the other kind of storage solutions out there, especially sort of the newer ones. Like we actually had Arweave on the show. Sam from Arweave was on like, I think maybe a year ago. And like they have a very different idea around this, but I'm wondering like how does the current version of Filecoin fit with, like also there's like the older ones like Chia and MadeSafe. These are things that we had mentioned on our earlier series. Where do you see yourself fitting? Are you using kind of some ideas from those? Do you see yourself as very different?
Yeah, I think we're pretty different. I think I think there's a subset of ideas that are shared broadly, you know, kind of like the basic, hey, you are going to hire a network. So some network's going to do resource sharing, and you're going to hire a network to store your data. It's kind of like broadly shared. But a few things are pretty different about us. So I think one of them is this proof of replication. So I think no other networks using proof of replication. They might start soon. This is kind of an advantage and edge that we have because we kind of created that field. But it's just one differentiating factor. For example, Chia is not quite letting you store people's data. It only is kind of like a proof of work, but a proof of like space-oriented chain. We also are I think the only one with kind of like this fluid market structure that is meant to optimize based on kind of an ask and bid structure where miners and clients are supposed to be able to reason about prices together and kind of then form deals out of that. And I think we're the only ones that are doing consensus backed by useful storage. So I think Chia is consensus backed by just a proof of space, but in our case, it's useful. Yeah, I think those are like three of the biggest differentiating factors. Then there's of course like the tight integration through Libp2p into IPFS and a bunch of other things where there's a ton of usage on top of IPFS already. It's going to be easy to just back up all of that data straight into Filecoin.
Cool. So you have sort of that advantage of like an already very, very used system that could be migrated.
Yeah. The one cool thing to mention is that IPFS is an open network. So now we've seen other groups start to build IPFS support. So I think like Storage and others are like now adding IPFS support, which is cool to see. Yeah, it's meant to be like a decoupled layer for that reason.
So to wrap it up, I want to bring it back to some of the things that we talked about in those early episodes. We had a look at the history of P2P, and we kind of concluded that P2P failed at some points. And we talked about reasons why it might have failed, like the UX was terrible. And honestly, though, like I think one of the biggest reasons is that, if we're talking about the early internet and it was decentralized, why was it decentralized? Well, everyone was running their own web server. Like when I was a kid, ran a web server in my house. No one does that anymore. And we're probably not going to go back to doing that. So that is where this world of incentives comes in, where I don't have to run my own server to be decentralized. I can pay someone to run a server for me in some regard, but I don't pay one single entity to do it. And my kind of ending question here is, what is possible in this new world of incentivized, decentralized storage?
It's a great question. And I'll probably start by saying like the last peer-to-peer summer, kind of like in the early 2000s, produced a bunch of like really good ideas, some of which succeeded more than others. So for example, I think like BitTorrent was pretty successful at a set of things, and it was kind of a pared down version of Mojo Nation and other things that came before it. And then the group that was doing Kazaa ended up building Skype. And then the kind of resource sharing around telephony ended up being huge and super successful until they got bought by companies that just didn't want to run the risk and didn't want to manage this like huge peer-to-peer network. And so they switched it to be kind of run internally. So there are a few successes, though, yeah, I think on the whole did not have like the massive lasting impact that the web had, or like, the early TCP/IP internet had. And so, yeah, I think when it comes to peer-to-peer, there's a few extremely difficult problems. And one of them is, this resource sharing and incentives. And I'll return to that in a moment. But I think others are simply just how hard connectivity is. So it's extremely easy to just rent a machine somewhere in the cloud and get like a publicly routable IP address and kind of like an always on system that kind of is easy to manage and so on. If you now have to deal with a bunch of computers that are running in who knows whose place, and they may be on or off, or all this complexity comes in, applications get potentially much harder to build unless the networking stack kind of takes care of it for you. And this is what we're trying to do with things like Libp2p and IPFS, make it so that you don't have to worry about kind of reasoning about those problems. But it's still kind of like substantially difficult for many use cases. I think one other big problem there is once you get into certain sizes of data sets for certain applications, you want to be able to run certain kinds of computation over that data, and having it sort of spread out across the world doesn't line up with the goals of some of those organizations, right? Probably the worst case of this, the worst version of this is the centralized social networks are building this huge trove of personalized data that then they're running kind of all this ad optimization code on top of, right? So it's like a bad case. But a good case would be, say, personal DNA or personal or like medical record type stuff where you're trying to run computation over all this data in like a secure, non-identifiable way for the purpose of finding important correlations between populations or things like that are like, can be useful to do better medicine or bio or things like that. So that kind of computation gets way harder in this distributed setting. But the good news is it gets much more user controlled, right? So if you kind of give your data out to somebody, even in the good case here highlighted with the medical record stuff, now you've given your data out to some other party and you no longer have control of it. You because you've kind of granted possession, you have like a limited control over it. And so this is where I think the cost is warranted, meaning like the cost of making it harder to build these applications is warranted because of the utility of that greater security that comes from it. Now, I think going back to the kind of the incentives question, yeah, I think like the big thing with all these resource sharing networks in kind of like the first wave was that they were either altruistic and kind of only scaled and worked when there was a different incentive layer, i.e. things like BitTorrent worked really well because maybe it's one entity trying to distribute game patches, or it's people trying to distribute material they don't want to pay for, right? So
or it's like having a really cool library of music and wanting to share that. Like I remember this with like Nutella. Like I was proud of what I was sharing.
Yeah, exactly. And so I think like there was like this other incentive structure around it that like allowed you to run that network. But I think once you start getting into high volumes, you encounter this kind of diminishing return where individuals won't want to run the thing themselves. And instead you want kind of a professionalized service. And it's in this professionalized service thing where you really want to use incentives. And I'll make it a case like very, very concretely. So I kind of think of this as open services. So think of open source as a set of kind of principles and licenses and so on for groups of people to come together and contribute to kind of a shared resource that is usually kind of like a knowledge good of some sort, like a code base or say the content in Wikipedia or something like that. And that open source works really well for that type of good because people can come and go and they can contribute to a thing a little bit and then move on. But open source does not work very well for maintaining services in that we haven't been able to see something with like near perfect uptime and like really high throughput or something like that come out of open source. Because kind of this volunteer-oriented thing does not lend itself well to, kind of being on 24/7 PagerDuty and working hard to scale the thing for users by users, right? So at that point, it turns into a job. Now, what's really interesting about the currencies is that they enabled the creation of a class of networks that are providing a useful service to the world, but they're doing so by hiring people with kind of an intra-currency that's based on kind of like the utility of the service itself. Mm-hmm. And so the best example of this is Bitcoin, where the Bitcoin network provides a service to the world of having a transaction processing system and say a store of value. And that service is like running 24/7 with like near perfect uptime. And it has certain transaction throughput that's probably not going to get better, but certainly like it's resisting all kinds of attack. A lot of people and organizations and nation states have tried to like bring it down, and that service is definitely up, right? Like Bitcoin is up all the time. And there are a lot of people working day and night to maintain it running because they're getting paid. They're basically hired by the network in a sense. And that's an extremely powerful thing. And this is effectively like a new class of thing that's now available where we can blend open source with economic incentives to produce an open service. And this open service thing now can run all kinds of utilities on the network. So think of the idea of a public utility as you would see it as kind of like water and gas and something like that in kind of like the real world. Now imagine that, but on the internet to run all kinds of important services, but now being kind of an environment where even adversarial parties are working together to maintain the service, right? So this is the case with Bitcoin and other networks where the miners are actually highly adversarial with each other and like do not want to help each other. They're actually often fighting each other. And yet they together produce this amazing service with a fantastic uptime, right? And so like that's like the power of incentives. So I think like this is where once we nail these structures and nail the UX around it, then I think these are definitely going to be the way that kind of computing resources are distributed. And I think all kinds of other open source services are possible. It's just that it'll probably take a while before all of this takes off. I think it's very early days on this. I think probably Bitcoin is sort of like GNU or Linux, and it's like one of the first precursors to a kind of like large explosion that will come. It's unclear exactly when that'll come, but I think a lot of UX and design challenges have to be solved before these things can really take off.
This has been such an amazing conversation. I hate to cut it off. I hope we can invite you back sometime and we can continue. I feel like there's all sorts of things we could talk about here.
Yeah, happy to. I think another time would be awesome. Thank you so much for having me. This was really, really fun.
Yeah, thank you very much.
And I'm going to say this, we've mentioned this decentralized storage series that we had started. It's a very old series. We are at a different point in our podcasting capabilities back then, but I will link it in the show notes. I think it was like the second episode we actually used this name, Zero Knowledge. So it's like very, very long ago. But yeah, thanks so much for helping us round it out.
Yeah, thank you.
Cool. And to our listeners, thanks for listening.
Thanks for listening.